Hi everyone, in today's video we are going to continue working with polynomial functions, and when given an equation, a polynomial equation, we're going to find all of the rational zeros. So in today's video we are going to learn about the rational zeros theorem so that we can apply it to find x-intercepts of the polynomial. We are going to use synthetic division to test a possible zero to verify that it is indeed an x-intercept. And then we're going to rewrite the polynomial using that zero as a factor and then find all of the other solutions to the polynomial. So let's get started by looking at the rational zeros theorem. Now, just to be clear before we get into this theorem, this method is going to be used whenever you're given a problem, a polynomial function, and told to find all of the zeros and you don't have any of the zeros to begin with. You don't have any idea of where to start. The rational zero theorem will help us find a starting point by giving us some possibilities for the polynomial zeros. So the rational zero theorem says if you have a polynomial function and it has integer coefficients, then every rational zero of the function has this form, p divided by q, where p is all of the factors or the possible factors of the constant term, that's the one that does not have a variable in the equation, divided by q, which is the factors of the leading coefficient. That's a sub n in this example. So we're going to list out all of the constant terms factors in the numerator, all of the leading coefficients factors in the denominator, and then simplify. And that's going to give us usually a really big list of possibilities. Now, the other thing that I want to point out here is that the really good news, the lucky news here, is that we are going to be able to use our calculator when we are finding all of the real zeros. So we're going to get a list of possibilities using this theorem, and then we're going to graph the equation in the calculator and look at the graph's picture to pick one strategically so we don't have to test them all to see which ones work and which ones don't. All right, so let's try an example of this. We have a polynomial function here, and the first thing we need to do is list all of the possibilities. That's using that theorem that we just worked on, which was p divided by q, where p is all of the factors of the constant term, and q is all of the factors of the leading coefficient. So let's make a list. The factors of 12, well, that's 1 times 12, 2 times 6, and 3 times 4. So that means that all of these numbers, both the positive and the negative version of them, can multiply together to get 12. So we're going to list them all here in the numerator. So that's plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay, so I've listed them there in ascending order. That's just going to make our simplification a little easier on our brains here in a moment. And now we need to do the denominator. Well, the leading coefficient here is 1, and the only two factors of 1 are 1 times 1, plus and minus again. So that means our denominator is going to be plus or minus 1. So if I divide a number, a numerator, by positive 1, it's just going to give me the numerator. If I divide it by negative 1, it's going to just change the sign of the numerator. And since I already have plus minuses up here, to write this in a simpler form, since I'm just dividing by 1, I have plus or minus 1, 2, 3, 4, 6, and 12. Whoops. Okay, so those are all of my possible x-intercepts. Now that's a lot of possible x-intercepts. Let's see, there are 6 there, but it's the positive and negative version, so that's 12 possibilities. We don't want to do that many synthetic divisions to find one that's going to work. So what we're going to do now is we're going to graph it in the calculator, and that's going to give us a rough sketch that we can then estimate. So let's pull our calculator over, and in the y equals, plug in this problem that we're working with. The problem says that x is raised to the third power plus 2x squared minus 11x minus 12. Oops, let's try that one more time. X to the third power, and then I'm going to get out of that power 2x, oh goodness, plus 2x squared minus 11x minus 12. Okay, so I've got my problem, my polynomial plugged in, so let's look at the graph now. And it looks like in my last problem I may have been zoomed out, so I'm going to hit zoom and then 6 for standard so that I can get back to the normal window. It's going to be a little bit easier here to make these estimates. Okay, so we've graphed it. I'm going to draw a rough sketch on my notes sheet and then we're going to write down some estimates. So let's see, it looks like the general shape of this polynomial is roughly like that. And it looks like there are 1, 2, 3 x-intercepts. So if we're just counting over on these tick marks, there's one at 1, 2, positive 3. There's one at negative 1, and that's 1, 2, 3, negative 4 is our other possibility. All right, so when we look at this list now, we have 3 possible zeros. X is equal to negative 4, negative 1, and 3. Looking up at the list of possibilities we found using the rational zeros theorem, negative 4 is on this list there, negative 1 is on the list there, and positive 3 is on the list there. So we can choose any of these 3 to test using synthetic division. Let's use the negative 4. It's the first one listed, so that's what I'm going to grab. You could use any of these with synthetic division. So I'm going to divide out that factor, that 0 of x is equal to negative 4. So I'm going to set up my synthetic division bar here. Then I'm going to use my coefficients from the problem, 1, 2, negative 11, and negative 12. And I'm going to divide it out now. So I'm going to bring down my 1. Remember, you're multiplying on the outside, adding on the inside. Negative 4 times 1 is negative 4. 2 plus negative 4 is negative 2. Negative 4 times negative 2 is positive 8. Negative 11 plus 8 is negative 3. And negative 4 times negative 3 is positive 12. That gives me a remainder of 0, which is good. That means it checks. Negative 4 is one of my solutions. So we are going to write a new polynomial function, f of x, where we've divided out this factor of the 0, negative 4. I'm going to write it as a factor, x plus 4, and then I'm going to use my coefficients down here from the synthetic division to write out the rest of my new polynomial, the depressed polynomial. So I have x to the second power minus 2x minus 3. Okay, and then our last piece after we write this new polynomial is to find the remaining zeros using whichever method works for this problem. So I am going to factor for this problem and use the zero product property because this piece here, this trinomial, is factorable. So let's go ahead and factor it. You are going to be using different signs with a 1 and a 3. We need to add them together to get negative 2, so that's a minus 3 and a plus 1. According to the zero product property, because I'm looking for zeros here, that means x plus 4 is equal to 0, x plus 1 is equal to 0, and x minus 3 is equal to 0, which means I get the x's negative 4, negative 1, and positive 3. So my solution set here is negative 4, negative 1, and 3. Those are all of the zeros of this function. And notice here that that answer, those zeros, it matches what my estimate was up here a moment ago. Okay, let's do another example so that you can kind of see everything worked through again. We have a function, a polynomial function here, and we need to find all of the x-intercepts, all of the zeros. So the first thing we're going to do is use the rational zeros theorem to list out all of the possibilities. Remember, that's p divided by q, and we need for p the constant term, all of its factors, so that's 1 times 20, 2 times 10, 4 times 5, and q is the leading coefficient. That one is just 1 again, which means that my denominator is just going to be plus or minus 1. Listing out all of my constant terms factors, I've got plus and minus 1, plus and minus 2, plus and minus 4, plus or minus 5, plus or minus 10, and plus or minus 20. Simplifying that, I'm dividing by 1, so I can just write those out as those numerators. Okay, so I have all of my possibilities here. Rather than checking all of them with synthetic division, let's graph in the calculator and estimate using that rough sketch. So in my calculator, I'm going to go back into the y equals. I'm going to clear out my old problem and put in x raised to the third power minus 8x squared plus 11x plus 20. I'm going to hit graph so I can see a sketch there. Okay, so let's go over here and draw that rough sketch. It looks like this one. Just something a little more like this time. And it looks like it has 1, 2, 3 x-intercepts again. Estimating there, roughly that is at -1. This one is at 4, and that last one is at 5. Okay, so now that I have my estimates, -1, 4, and 5, we're going to choose one to test using synthetic division. I think this time, just to show you that they all work, it doesn't matter which one you pick, I'm going to pick 4 this time, the one that's in the middle. So I'm going to divide out the factor of x minus 4, so I'm using that x is equal to 4 solution as the divisor here, and I am going to put my coefficients 1, -8, 11, and 20 inside of my synthetic division. Okay, so we're bringing down the 1. 4 times 1 is 4. -8 plus 4 is -4. 4 times -4 is -16. 11 minus 16 is -5. And 4 times -5 is -20. That's great because that means I have a remainder of 0 and it checks. That means 4 is one of my solutions. So let's do our last piece here, writing a new polynomial and finding the rest. I'm going to rewrite my polynomial with the factor that I know, this 4, so that's x minus 4 when I write it as a factor, and then I'm going to use my new coefficients to write my new depressed polynomial. That's going to be 1x squared minus 4x minus 5. Okay, looking at this one, I'm going to factor this one again because this is a factorable trinomial here. So I've got x minus 4, and I'm going to use a 1 and a 5 when I factor these. The 5 is going to be the negative, and the 1 is going to be positive to get me that -4 when I add them together, which means that my solutions are +4, -1, and +5. Verifying your work here, notice that those are the same ones that we estimated a moment ago. Okay, so now the last part of the notes sheet is a now you try. In this one, I'll give you a hint. When you get down to step 4 here, it is going to be a prime polynomial, so you're going to need to use the quadratic formula to solve that one and get these final solutions. So let me give you the quadratic formula just in case you've forgotten, because it's been a little while since we have used quadratic formula. So the quadratic formula is -b plus or minus the square root of b squared minus 4ac, all divided by 2a. So when you get down to step 4, use that quadratic formula to help you solve. In this video, you have learned about the rational zeros theorem and how to apply it to find a big list of possible x-intercepts. Then we graphed them in the function in the calculator so that we could choose some more strategically. We used synthetic division to test one of those zeros from the graph, and then we rewrote the polynomial function using the depressed polynomial to and one of its factors to find all the rest of the solutions using one of those methods that we've worked on in chapter 4. So give that now you try a try.